So, hello everyone and welcome to day 2 of the first week of the Fair February. Today we continue with the series of talk about computation and health. So we have two speakers, Dr. Erisa Terolli and Dr. Ignacio Segovia Dominguez. We'll start by Erisa, and before introducing her, I'd like to say a couple of Q&A session. So Erisa will take questions throughout the talk. So you can just raise your hand or better unmute yourself and ask the question. If you're not able to see or you're not able to unmute, just write the question in the chat, and at the end of the talk, we will resume and write them to the speaker. So let's start. Dr. Erisa Terolli is a postdoctoral researcher at Max Planck Institute for Informatics in the Database and Information System Group. She got her PhD from Sapienza University in computer science, and she graduated in 2018. Her main interests are information retrieval, knowledge discovery for biomedicine, graph mining, and computation social science. She is a Google Anita Borg scholar, so it means that she is actively involved in organizing community enriching events for reducing the gender gap in computer science. So Erisa, I think you can now share your screen.
Yes, thank you for the kind introduction. Can you see my screen now?
Yes.
Great. Yes, so hello everybody. First of all, thanks to the organizers for inviting me to this nice workshop. I am Erisa Terolli and I am a postdoc researcher at Max Planck Institute for Informatics. In today's talk, I'll be talking about focused query expansion with entity cores for patient-centric health search. This is a joint work with Patrick Ernst from Amazon, Berlin, and Gerhard Weikum from Max Planck Institute for Informatics. The results of this work were kind of published or presented at the International Semantic Web Conference in 2018, and the paper was selected as the best paper runner-up. Okay, so let's start with the core of the talk. The internet provides a wealth of online content about health topics. Nowadays, a lot of users turn to health forums or health online communities to seek advice from either doctors or from other peers with similar cases. These online health communities serve as a source of information for people with medical conditions. The way that these online health communities work is that generally users post questions and other users, which might be normal or layman user or even specialized medical kind of staff like doctors or nurses, would go and reply in a community question and answering manner. There exist a lot of tons of health online communities, starting from general health communities that talk about 100 different diseases or conditions, but we also have some kind of very specialized health online communities that talk about a specific disease, like a diabetes online community or even, I don't know, asthma online community. But some of the most prominent and most used online health forums are eHealth Forum, health boards, which are, both of them are US based. And on the other side, we have Patient, which is a British online forum. The way that these online forums work is that a typical post that a user would go and write there includes a short question. It's shown over here on the picture, on the screenshot on the right. There is a short question, which is a short and concise description of the main problem that the patient has, and then followed up by kind of a case description as shown over here, where the user would go and would elaborate in details about the medical condition or the question that he wants to know more or he wants to ask the community for. So as I said, on one side, we have these kind of big online health communities where normal user would go and write kind of natural style text asking questions. And Of course, this kind of knowledge is unstructured because we just have pieces of text coming from users. But on the other side of spectrum, there exists a lot of structured and high quality data. One example of such representation of high quality data are knowledge graphs. And a knowledge graph represents a collection of interlinked description of entities that can be real world objects, can be abstract concepts, or even events. To make things easier, I invite you to look at the picture over here. In the graph shown over here, we have nodes that represent entities such as we have Paris, for example, we have city, we have Eiffel Tower, and then we have Mona Lisa. And then we have also connection between these entities that represent how these nodes are related to one another. For example, we have an edge between Paris and city uh, with kind of an attribute is, which indicates that Paris is a city. Or we have that, for example, Eiffel Tower is located in Paris. So again, knowledge graphs are some kind of ways of representing high quality structured data where we have nodes that represent entities or concepts, and we have edges that represent the way that these concepts are related to one another. And you can think it as kind of a labeled graph, both on edges and nodes. So while there exists a lot of kind of general knowledge graphs, luckily for us that we are working in kind of extracting knowledge from biomedicine, there exists a lot of work on building biomedical knowledge graphs. One very kind of well-known example is No Life, which was kind of constructed by some other members of my current team. And the way that these kind of biomedical knowledge graphs are populated is that they extract medical facts from trustworthy sources on top of the manually curated kind of graphs published by professionals. So the way that they are kind of enlarged is that we have some really small knowledge graph coming from doctors that are manually kind of created. Doctors go and create nodes and create relations. But of course, these are very kind of small in size. In order to somehow to populate with new facts or with new biomedical knowledge that comes from trustworthy sources, the way that kind of the community is doing is that they go in very kind of in, let's say, journals that they have a high impact, or they go in encyclopedic pages that are trustworthy, such as WebMD or Mayo Clinic, etc. They go and they extract entities or concepts. They also extract relations. So as you can see in this picture over here, using some kind of typical NLP pipelines that I won't go into details. People go and extract Crohn's disease, increased risk for developing colorectal cancer. And since this kind of knowledge comes from really kind of high quality articles, we can assume that there is a relation between Crohn's disease and colorectal cancer with the type of creates risk. While we have these resources of structured and unstructured data, medical data, the question that we asked ourselves is that how can we use this curated knowledge coming from trustworthy sources to improve the process of mining the discussion boards? So what we want to achieve is that we want to get a better insight on what's going on within the online forums. But since on the other spectrum, we have this high quality structured data, how can we make use of this high quality structured data to better understand and to better mine insights or knowledge from online health forums? So for this reason, we started our effort on mixing this type of data to improve searching over health communities. Normally, all health forums or health communities provide searching functionalities beyond the common question and answering theme. So on top of just going and writing a question, you can also go on the search bar and write a query related to your medical condition and see what results would the platform give to you. However, searching over health forums tend to be of very poor quality, since the retrieved results are often too broad on one side and they are not focused on the patient's specific needs. So because the queries are very short, they do not include all the personalized information that comes from the medical description of the patient. So in these short queries, we don't know what symptoms the patient is having or what other kind of previous diseases he has been suffering or what kind of medication the user is taking. So let's take an example. For instance, the query aggressive attitude in Alzheimer patient, the one that we explained before and we are going to use throughout the whole presentation. Might return results that are not focused on the explicit user intent, that would include all the kind of defined details that comes from the description written in the post. So even though the initial question of users tend to be short, the case description, as I said, presented in the body of the post contains a lot of useful information because it describes the patient diagnosis and then symptoms that he is having, test results that he has done previously, the drugs that the medication that the user is taking, but also kind of other self-observations. And since there is such details describing the medical case of the current patient buried in the post body, as shown over here, one straightforward approach in information retrieval to improve let's say, the performance of the ranker is to go and just grab all the medical entities that are present in the post and then expand the initial query with all of this entity. So for example, our initial query, aggressive attitude in Alzheimer patient, would be expanded, or like for the ones that are not very familiar with information retrieval, query expansion is you have an initial query and then you create a bigger query, but by adding extra information, which we hope that it will make the query kind of better. And in this case, the initial query, aggressive attitude in Alzheimer patient, would be expanded with medical entities like dementia and brain and hallucinations or brain disorder or delusions, with all the medical entities that are extracted from the user post. However, query expansion has been shown to be one of the kind of smartest solution in information retrieval. The expanded query in this specific scenario tend to be broad and away from the user intent, as user might include multiple medical entities that are not directly related to his main concern. So imagine a case when a patient would go and discuss about the disease that he had when he was 5 years old, or he might talk about something that one of his family members is suffering. And the diseases that one of his family members is suffering are not directly directly related to the main concern of the patient. Of course, there are some diseases that might be kind of passed through the family, but this is not always the case. Another disadvantage of this query expansion approach is that the entity selected for expansion does not incorporate any degree of informativeness. So we pick all the medical entities and we cannot say which of the entities is more relevant to the query. So for example, for an Alzheimer patient, dementia is more relevant than oxygen, for example, or than exercising, or than some other entity. And the third and the final disadvantage of this approach is that while we make use of all of the entities that are present in the post, we do not make use, or we do not use the relations that exist between this entity. So all the relation presented between the entities that of course might contain some very useful knowledge and very useful information are omitted or are not considered. To overcome all of these kind of problems or disadvantages, what we have done is that we have introduced a new method called entity core expansion, or short ECHO, which serve as a refinement step that identifies the most relevant and coherent entities for focused expansion. And in this slide over here, I am showing a simple architecture of the method. And how it works is that the initial query of the user will be expanded with all of the medical entities that are present in the post. And then the most important step is the box shown in light blue over here. So first we expand it with all of the medical entities, and then we want to shrink the medical entities and to get the best or the most informative entities that will give us a better query. In other words, is that we have this long expanded query, and we want to extract the core of this entity. So just pick the most important subset of entities that will be used to expand the original query. And while we somehow computed the core of the entities, the initial query will be expanded only with this kind of subset of entities, and then the final query will go and search over the kind of the corpus, and will give us back a ranked list of results. So if you have any question, because this is one of the kind of the main slides, just unmute your mic. Sure.
Yeah, my question is, while you do the focus for picking the entity core, are you ranking the entities you extracted before and so assigning different weight according to their importance for the query and the entity they refer to, or you discard those that you are not interested in?
Oh, yeah, this is a very kind of important question, and I'm going to explain how we pick the entities in the next slide. Okay, so yeah, this is the main kind of overview of the system. Now, the natural question that arises, and Christina actually asked, is that how do we compute this entity core? So how we pick this important or most relevant entities? Before explaining on how to compute the entity cores, I would like to define the concept that we have called a patient query graph. And a patient query graph is a graph in which the vertices represent all of the medical entities that are present in the post, and edges represent all the relations between these entities in any kind of high quality biomedical knowledge graph. So for example, for the example of the Alzheimer patient, we have converted the post into this patient query graph, where we have entities like Alzheimer and then dementia and memory loss. But of course, we also have relations like dementia causes Alzheimer, or memory loss is a symptom of dementia. Once we have generated the patient query graphs, the problem of finding the entity cores for focused expansion can be seen as the problem of extracting the most informative subgraph from the patient query graph. So we have converted the post into a graph, and then we cast the problem of computing the entity cores by extracting the most informative subgraph in this graph. So one kind of simple and straightforward solution, the problem of extracting the most informative subgraph from the patient query graph, first can be casted as a minimum cost Steiner tree problem, where we find the minimum cost Steiner tree that would connect the entities of the initial query. However, this approach comes with some limitations, as Steiner tree must include they must include all of the terminal nodes, and we are not sure that all of the terminal nodes are kind of important or informative. And all of the terminal nodes are exactly the entities in the original query. And then the second disadvantage is that the Steiner trees are not flexible on selecting entities based on their degree of informativeness. So for this reason, we have casted this problem into the famous price collecting Steiner tree problem, where given an undirected graph G with vertices V that are associated with non-negative rewards and edges that are associated with non-negative cost. A price collecting Steiner tree is a connected subgraph that maximizes the sum of rewards of the picked nodes minus the sum of cost of the selected edges. In our particular case, the reward of a specific node is represented by the TF-IDF score of that node in the subforum where the question is posted. So for example, if we want to compute the reward of dementia, we go and compute the TF-IDF score of dementia inside the Alzheimer's subforum, because this question was posted in the Alzheimer's subforum. And the cost of each of the edges we have defined as 1 minus the PMI score of the entities that represent the endpoints of the edge. So if we want to compute the cost of the edge between dementia and memory loss, we go and we say that the cost of this edge is 1 minus the PMI of dementia and memory loss, always inside the specific subforum where the question is posted. Using these weighting scores for nodes and edges in the patient query graph, the price collecting Steiner tree for our Alzheimer example highlight like the price collecting Steiner tree is highlighted in green, where you can see that entities like hallucination and memory loss and dementia and confusion and the drug Aricepts are picked by the price collecting Steiner tree, which indeed are really entities that are very informative for the specific medical case of the current patient. And again, after explaining the patient query graph and after explaining on how to compute the entity core, what our method does is that it gets the initial query and it will expand it with only the entities that are kind of selecting in the price collecting Steiner tree. So in the example of the Alzheimer, the initial query will be expanded only with the entities shown in green. So there are two main advantages of the echo expansion. So echo expansion would enforce, first of all, the coherence between entities in the query to counter topical drift. So it will mostly focus on the main topic that the patient is discussing. And the second, the conciseness of the query itself by removing the entities that are not in the core of the query intent. So of course, up to now, everything looks fine. It seems like it's a very simple solution, and it seems like it should work. However, to test the efficiency of the echo method, we have built a prototypical search engine for querying health forums based on Elasticsearch. For data, we have loaded and indexed over 21 million health documents that include health forum discussions, PubMed articles, encyclopedic pages, and also clinical trials. And for each document, we have indexed the title of the document, the content, the full content of the document, and also we have annotated each of the documents, and we have extracted all the biomedical entities that are mentioned in this document. And for testing purposes, we have selected 20 diseases with high coverage, including asthma, diabetes, blood pressure, depression, etc. And for each disease, we have manually identified 5 typical user posts, which will serve as queries in our experiments, making a total of 100 taste queries. And then of course, we have compared our method with existing competitors, such as straightforward keyword baselines, when the query is just the title or when the query is just the concatenation of the title and the post. Another competitor is the entity expansion, when the initial query selects all of the entities without cherry picking them. And the third competitor is the Steiner tree expansion, where the initial query is expanded with entities that are present in the minimum cost Steiner tree. And of course, all of these competitors are compared with our entity core expansion. But as you guys might know, one of the main problems of evaluating this kind of approaches is the lack of label data. So we suffered a lot on gathering label data because either companies do not share this kind of information, or you cannot even know who owns or who has this kind of label data. So to gather relevance judgments, we have conducted 2 big crowdsourcing experiments. The first one includes layman users, because this searching is targeted to them. So we have conducted a crowdsourcing experiment in Figure 8 platform. And then on top of that, to validate the data, or to make sure that the approach makes sense, we also conducted a second crowdsourcing experiment, but now the judges are certified medical doctors. Of course, we have labeled a sample, like a subset of the data, with medical doctors due to their limited time, but also super high cost. And what either a layman or a doctor do is that they are presented with the query, and they are presented with a document, and they have to say whether this document is relevant for the given query or not. With the gathered judgments, we have compared each of the methods across different kind of well-known metrics, such as precision, mean average precision, and NDCG, both at 5 and at 10. As can be seen from this two specific table, we see that even a simple entity expansion, when we do not kind of select carefully the entities that we want to expand, improves the results significantly. However, the focused expansion would provide, that is kind of provided by our echo method, makes the results even stronger and outperforms all of the other baselines significantly across all metrics. And these results are the results coming from the crowd, from normal people who maybe do not have any medical background. And as I said, to make things, to make sure that our method is better than the rest of the competitors, we conducted this smaller scale crowdsourcing experiment with doctors. And even in this case, the ECHO methods yields additional benefits in the retrieval performance, with significant gains when gathering assessments of relevance by medical professional. As you can see, we see that the scores given by doctors are lower compared to the crowd. And this comes from two specific reasons. One, of course, doctors are more skeptical on saying that a post written by another user is relevant, or is relevant for a question written by another kind of normal user. And second, we have considered a document to be relevant if both of the doctors kind of marked it as relevant. Since we weren't able to find three different doctors to label the data, we found only two, and then we considered to make sure, we said that the document is relevant if both of them say that this is relevant. So, but even under this really strict, let's say, filtering or requirement, we can see that the entity core expansion would provide better results than the other baselines. So to conclude with, in this project, we have addressed the underexplored topic of search over online health communities. We have devised simple but powerful methods for focused expansion, exploiting entities and relations existing on some medical knowledge graph. Finally, with an extensive set of experiments, we have demonstrated the viability of our approach and its benefits over other baselines. And I want to conclude with a very simple generalization kind of approach. In this work, we have focused on searching health communities and also clinical trials, as health is by itself is an important domain with high impact. But however, in general, our methodology can be adapted to other domains as well, such as finance or food or travel. So for example, we can address a travel discussion forum where user would go and ask for exchange experiences like visa issues or a sightseeing location or paths or local food and culture. Since this kind of discussion are subjected to individual preferences, so that the ranking result by personal relevance is important, we believe that our approach would perform really well. Of course, in this case, we have to use travel-centric knowledge graphs. And then after finding the travel-centric knowledge graphs, we can use the ECHO method for focused query expansion. So thank you very much for your attention. These are my contact information. Feel free to drop me a line. And on this picture over here is a picture of the MPI building. We are constantly hiring interns and PhD students. So if any of you guys want to apply for an internship or want to do a PhD in Germany, just drop me a line and we can see what we can do. Now I'm open to questions.
Thank you, Erisa, for the talk. It was really, really interesting. And are there any questions for Erisa? So you actually answered a question that I had in mind once I saw that the scores given by the doctor were a bit lower than those from the layman users. Mm-hmm. So my question is, in general, if you know, if it's just a curiosity more, if doctors are willing to tell patients that sometimes they may go online to do a pre-screening of their symptoms before contacting them, and if you are actually planning to propose and run this search engine you built up on some platforms that you mentioned in the beginning.
So normally I've never I never kind of had such an experience where a doctor would say go into online health communities and search. What the doctors advise not to do is to go and kind of self-diagnose yourself in Google or in other platforms. This is they strongly advise not to do that, because then people are focused, like they have self-diagnosed, and when the doctor says something different, they tend not to believe. However, what I've seen, these online health communities are very good for mostly for even for support. So people find similar after being diagnosed, people go there and find other people who are suffering from the same the same condition, they build some kind of a support community. The other part of the question, whether we are interested or we want to make some kind of to release this search engine for patient to go and search. This is very delicate situation, because first we want to really make sure that the quality of your ranked results is really good, um, and you don't want to somehow you don't want to put more pressure on patients that they really have. What might be something kind of maybe in the future, I don't know, I'm just thinking out loud now, is that you can start this small search engine, and you can kind of ask medical students just to try it, and then by using some kind of pseudo relevance feedback, you can improve. So like while they are clicking on important documents that they think they are relevant, you can go and you can improve your ranker. But at this current stage, I think it's not ready to go and just open it to the public. And the other problem is that, as we know, in Europe, the patient information is very, we have to be really careful, because you cannot find this kind of information from hospitals.
Thank you. So thank you again, Erisa.
Sorry, Erisa, I have a question.
Sure.
Is it possible to expand your work into probabilistic nodes, such that instead of having graph knowledge, you will have like probabilistic graph knowledge? I mean, I'm thinking in those areas where there is some uncertainty about anything, about the information, so that you would have a distribution on each node, and maybe you could do probabilistic inference on that graph. Is that possible, or?
No, I think this is it. From our approach point of view, it's possible, because then you just kind of recalculate the way that you want to pick entities based on these distributions. However, I think the domain doesn't allow you to have a knowledge graph that is not like of the highest quality. So you don't want to include facts that are 40% true, for example. Okay. So, but I believe that in other domains like travel, or let's say even food or music, this is I think it's feasible, and it's a really nice idea, actually. I haven't thought about it, but in health, I wouldn't suggest to do something like this, because even even in this particular case, when we get really high quality relations from the knowledge graph, we had a lot of problems with the reviewers. So even the paper got award in the end. So we had a series of rejections, because people were skeptical about the quality of the knowledge graph, which makes the domain very sensitive, and it can create other problems. But this is a nice idea. I think I should think more about that.
Oh, thank you.
Thank you, Erisa, again.
Thanks.
So I guess we are ready for our next speaker, Ignacio. So I will, Ignacio will take question at the end of the speech. So if you have some, just write them in the chat, and we read them out at the end of the session. So Dr. Ignacio Segovia Dominguez is a research fellow at the University of Texas at Dallas, and is a visiting researcher at NASA JPL Caltech. Is developing novel analytic tools for modeling and forecasting dynamics of climate-sensitive infectious diseases. He got his master's and PhD in computer science from the Center of Research in Mathematics in Mexico. Its agenda is focuses on topological and geometric methods in statistics and machine learning of complex dynamic networks and evolutionary computation. Jointly with JPL, NASA is currently working on methods that are aiming to improve the understanding of hidden mechanisms behind air quality and atmospheric condition and COVID-19. So Ignacio, you have the floor and you can start when you want.
Oh, thank you for that nice introduction. So, first, on behalf of our team, which is a big team, many thanks for this invitation to present part of our ongoing research in COVID-19. Actually, this work is a joint research between University of Texas at Dallas and the NASA Jet Propulsion Laboratory, Caltech. Today I'm going to present an overview of our current methodologies to forecasting the COVID-19 progression and possibly next hotspots. Just let me highlight that actually the results from this talk are part of a much larger project in which we aim to investigate the impact of weather conditions and air quality on COVID-19 transmission rates and well, also another topic important, which is clinical severity. Yeah. So as of yesterday, there are more than 101 million confirmed cases and over 2.19 million deaths due to COVID-19. And actually, SARS-CoV-2, which is the virus that causes COVID-19, differs from other viruses such as influenza, SARS, and MERS in different ways. For instance, in its response to weather conditions, including temperature and humidity and others. So last year appeared numerous contradicting studies on the linkage between atmospheric variables and the progression and the mortality of COVID-19. And in this research, our objective is to evaluate the utility of modern approaches such as the topological predictors on NASA satellite observations to model the current and the future COVID-19 spatio-temporal progression. That's objective. And also, in part of that objective, we like to focus on the progression of the severity of the disease. This new approach allows us to investigate relationships between weather condition, also air quality, which is very important, and COVID-19 dynamics. And we are trying to merge deep learning models with topological data analysis features and tools. So just trying to motivate this research, well, to the best of our knowledge, there are these contradictory studies on the linkage between weather conditions and the progression of COVID-19. And as you can notice here, in several papers, some researchers claim that atmospheric variables have an impact on the transmission of COVID-19, while others actually highlight cautiousness to these conclusions. So in most of cases, these studies are limited by applying simplistic linearized relationships, but also by the lack of uncertainty quantification. And let's say there is still a low amount of COVID-19 records in comparison with other diseases. So it's very challenging to work with that amount of data. But well, another source of motivation actually comes from the data science, because there are new attempts to forecasting the COVID-19 time series via deep learning methodologies. To the best of our knowledge, there have been various approaches using all types of neural network learning methods. A few of them integrate additional covariables in their learning steps, while the rest actually do not even consider these other covariables. So for instance, here you can see the joint effort between Google and Harvard, which result in a deep learning method, which includes an extension to the standard SAIR model that actually have additional compartments for undocumented cases and hospital resource usage. This is one of the few efforts which consider covariates in the modeling steps, but actually most of current efforts using DL focus on applying neural networks on the crude time series. And particularly, they do not model complex relationships between weather conditions and the COVID-19 record. So based on that, our current work is driven by these research questions. Understanding the impact of atmospheric conditions and air quality is urgent and actually is critical. Not only in terms of efficiently responding to the pandemic, but also in terms of forecasting next hotspots and potential wave occurrences. Let's hope that there are not so many in the future. So with this project, we aim to meet the decision makers' need to allocate scarce medical resources for COVID-19 hotspots because as you know, we need to work on, we need to prepare on an adequate healthcare response in areas with expected higher clinical coronavirus severity, or even to do plans for vaccine allocation. How we do that? So that's one of the things that we would like to answer with this research. So to address these queries, actually we formed a research team with members of UT Dallas and NASA JPL. Julia, Jill, and myself, well, we are statisticians and applied mathematicians and computer scientists with expertise in deep learning and topological analysis. Rishabh Wang, Shiwa Shen, they are data scientists. Christoph Gorski is our cosmologist, and he has expertise. He has expertise in multi-resolution analysis. And Gil Lee and Michael Garage are our specialists on climate scientists. As I mentioned earlier, today's presentation is part of a major project. So let me talk about the type of data we are using, although in our pilot study, which I am going to present later, we use mainly data from weather stations. We use observations of surface, air, temperature, and relative humidity from the atmospheric infrared sounder, AIRS, and the cross-track infrared sounder, CRIS. Surface, air, temperature, and relative humidity may affect the airborne survival of coronaviruses, and AIRS and CRIS actually have provided nearly continuous global coverage on those of these two key variables over many years, even in places where the ground-based observation network is sparse. So it's a really good source of information. But also we need also source of information, but from the COVID-19 side. So about the COVID-19 disease progression, we use the MIDAS database and archives of parameters estimates, but also the Job Hawkins data repository, which is publicly available, and datasets also publicly available in its state repositories. For this research, we want to merge deep learning, but also with topological data analysis. So let me talk a little bit about this TDA, this topological data analysis. Or the core of our approach consists in extracting this topological information from NASA satellite observations and build a geometric deep learning method to model the current COVID-19 spatio-temporal progression. we want to focus on both the spatial information, but also the temporal information. And also, we want to use that for spread, but also for clinical severity of the disease. In particular, we extract temperature, humidity, and aerosol optical depth. Our working hypothesis is that the limitation of conventional approaches is due to the sophisticated, non-separable spatiotemporal dependence structure of atmospheric temperature and humidity that has been researched for previous works in literature. And actually, the adaptation of deep learning to these various objects in non-Euclidean domains is currently experiencing a growing interest within the machine learning community. It's a hot research, so there is a plenty good opportunity here. So how do that? Well, applying TDA in satellite observations actually bring us key benefits. Let me just mention 3 of them. With TDA, well, provides property invariant under continuous transformations, such as stretching, bending, and squeezing. Also, the TDA summaries do not depend on coordinates, which is very good. We get a compressed representation of shapes characteristics. For instance, let me explain a simplistic example of using TDA on data. Please observe these 4 images on the World COVID-19. Notice that all of them have the same topological features, 9 connected components, and 3 holes. These 3 holes are in O, D, and 9. So usually in this context, we name connected components as 0-dimensional features and holes as 1-dimensional features. Maybe it would be better to watch something more dynamic. So in general, we describe shapes of point clouds or even complex networks via analysis of simplicial complexes and then track fluctuations of the resulting topological signatures over time. Let me show you this example. This is a point cloud. And for instance, in this video, we have a radius increasing ball centering in each point. When 2 balls touch each other, well, we mark we mark it as a new connection, new connected component. So let me pause this. As the proximity parameter epsilon increase, some connected components persist while others disappear, as you could notice here in this barcode. This is called a barcode in the bottom right. Also, the times of appearance and disappearance of topological features actually are conceived as points in persistent diagrams, as shown here. So we can compress the structure of these point clouds in these persistent diagrams. So and these persistent diagrams could provide us with a signature of these point clouds given the epsilon parameter. Something interesting, for instance, about this approach is something that you notice here with the hole of letter D. This is also detected using these methodologies. Of course, TDA also can extract any dimensional topological features, not only 0-dimensional or 1-dimensional. Actually, it could go to any dimension. That depends on the simplicity we are using. But what I'm trying to say is that, for instance, here, hole, notice that is detected because we notice that these features, which is actually a hole, is persistent. It burns a deep value in epsilon and keeps continuing, keeps living over there. So let me go to the previous persistent homology works similarly on other abstract objects, not only on point clouds. For instance, it could also work on graphs. The key difference is that 2 vertices of a graph are considered connected when each corresponding edge weight is below an epsilon value. So actually here we compute, instead of having a ball on each point, actually we try to detect when there is a connection based on an epsilon value that increases over the weight. So so the persistent homology, which is the tool that we're playing right now, tracks emergence and disappearance of these n-dimensional topological features as the scale parameter epsilon increases. Again, the pair of scale values of birth and death actually are these to the point characteristics on the persistent diagram over here. So our research group here at UT Dallas actually works heavily on applications of TDA on graphs, on point clouds, but also on graphs. So that's good because we could use some of our current tools in any graph and extract distinctive topological summaries. But now, I mean, TDA is an important research area now, but that area has been used for infectious disease before. Well, yes, previous studies have shown that Euclidean-based analysis of similarities between epidemiological curves for seasonal influenza types in Portugal and in Italy delivers actually inconclusive results. But when you supply this analysis with topological information, you get important insights on the similarity of fluid dynamics and secondary attack rates. And more recently, forecasting vector-borne climate-sensitive diseases such as Zika was demonstrated to be significantly better in models that use non-Euclidean distances to analyze weather and disease data. And in this context, well, and to the best of our knowledge, there is not any TDA research to forecasting COVID-19 dynamics yet. So we are working on also the results of our research are going to add something new in that trend. Now, to verify the effectiveness of adding these topological summaries for forecasting the number of confirmed cases on COVID-19, we performed a pilot study on North Carolina and also on California states. Now, let me give you an overview of our methodology for this pilot study. Here we have some weather stations, but also in each county, we have the number of confirmed cases of COVID-19. So we have two sources of information actually. From these weather stations, we can get environmental variables. And these environmental variables, well, based on distance and the variables that we extract, we use this information to create some graphs, which allows to have a dynamic network, time series of graphs. And using filtration and persistent homology, which is part of the TDI model, we got these persistent diagrams, which are inputs, are or topological features that we take as input for a learning model. So we have two sources actually. We have these country level cases, but also we have these topological features. And these two inputs help us to train a recurrent neural network. And at the end, we got a county level forecasting. So some technical details on this study. Well, there is policy data available. We took policy data available from COVID-19 and data from the National Center of Environmental Information. We choose environmental variables like the dew point, visibility, and temperature. We are using 66 meteorological stations. We have a training period from April to July, and that's for North Carolina. And this period is the whole month of August. But for California, actually we have from April up to August, and this period is September. And there is there is also a difference there. We are doing a month ahead forecasting. In particular, we perform their predictions. Well, we summarize the persistent topological features on each graph. I mean, here below in the TDI model, using a Vittori-Rips complex, and we are using topological features of 0, 1, and 2 dimensions. It means that we are able to detect connected components, holes, and voids on the dynamic network. In particular, for this recurrent neural network, well, we are using a well-known LSTM. And after the training step, well, we are able to get this controller forecasting for the test period. These are two maps of all the weather stations that we are taking. There are 66 weather stations, and let me tell you that we focus mainly on two cases. For North Carolina, we focus on number of confirmed cases. That's the variable that we are trying to forecast. But for California, actually, we focus on hospitalization numbers, which could tell us something about the severity of the disease. And actually, I am part of the Latino researchers community, and these hospitalization numbers actually are of special interest due to the difference on COVID-19 severity in different races, as has been published available by CDC. So that's one thing. Now about the architecture on recurrent neural network. Well, these recurrent neural networks are better suited for time series. Current architecture includes 3 stacked LSTM models. We have this number of units in each layer, and at the end we have a dense layer that allows to get the output of depending on the number of counties. And yeah, that's the architecture of our model. So in our experiments to verify this, actually we compute the RMSE, the root mean square error. We explore actually 3 different cases, only using the number of confirmed cases as input, using the number of confirmed cases plus environmental variables, and using the number of confirmed cases plus topological summaries. We want to figure out if adding these topological features actually give us something additional. And on North Carolina, we noticed that these graphs are showing that RMSE actually there are 28 counties. Well, if we contrast the addition of topological summaries versus the other 2 cases, there are 28 counties where we improve the results against both other cases. That means that adding the topological features is giving us something additional. Based on these results, we can say that forecasting performance of new daily COVID-19 cases at county level can be substantially improved upon integrating these topological summaries of atmospheric variables. However, we noticed that in some counties consistently there are some higher errors than others. Truly, it is related to other hidden variables that we are not considering in our current data set and modeling. So some of them could be population size, percentage of ruralness, percentage of fair poor health. We plan to integrate such variables in our current modeling. But let me go to California. So in California, as I mentioned, we perform similar experiments using hospitalization numbers. And so we are doing daily data. And here, actually, it is very clear that adding topological summaries in the depth learning model really improves the results. Please focus on the top right figure. Notice that in general, we reduce the distribution of the amount of root mean square errors at county level as shown in this box plot. Similarly to North Carolina, we are planning on integrating other hidden variables to our current modeling. So this is a part of the study, of course. from here, we have some conclusions. Our current studies actually suggest that we are on the right track by extracting these topological summaries of weather condition variables and using them in our learning steps. We will evaluate a relationship between air quality and COVID-19 clinical severity. Of course, we are planning on expanding this analysis to other states, or even compared to the conclusions to other forecasting horizons, or even spatial resolutions. I mean, instead of county level, maybe state level, maybe country level, etc., and other temporal resolutions. So we are working on integrating other hidden variables, like I mentioned, socio-demographic factors or many others. And currently, this is, well, we are doing more sophisticated approaches based on GPL, GNN, and recurrent networks or non-structured data, which could give us even better results. But with this pilot study, at least we could say that it seems like using these TDA tools actually add something new in the learning process. Thank you, and again, on behalf of our team, many thanks for attending this presentation, and please feel free to ask any question or contact me.
Thank you, Ignacio. So are there any questions for him? So I actually have a couple of questions. The first question is, when you do the two models, one on the number of cases and the other number of hospitalization, I wanted to know whether the topological feature you're adding to the model are the same.
Oh, no, they are similar because those features, I mean, we are using the same parameters, but the persistent diagrams that we got for each one actually are different because for one, the location of the stations is different, as you can see here. But although we are extracting the same variables on each weather station, the construction of these networks actually to construct these networks, we use some weights in each edge. So to get those weights, we compute a similarity measure, and that similarity measure actually give us a value depending on the values obtained at each day in each weather station. It means that although we are using the same parameters, we are obtaining 0, 1, and 2-dimensional features. The persistent diagrams that we get in both cases are different. Now, we need to do further analysis to verify if using the number of confirmed cases give you widely different topological features in contrast with topological features obtained from hospitalization.
I see.
So that's one thing that we are currently studying actually, and we are working on it.
And the second question was instead more about the interpretation of the models. So we saw that the prediction and the correctness of the model for the hospitalization seems a way better than the prediction of number of cases. So I was wondering whether you or your team, of course, had some idea of why the model works much better for hospitalization.
That's actually a very, very good question. Our hypothesis is that actually the weather condition have an impact on the severity, and when you use the number of cases just tell you that some people got the disease, but they don't give you information about who is really having trouble or who could die. And apparently this difference, this big difference between North Carolina and California, is showing us that the weather conditions actually have an impact on the possible result on the hospitalization, or in general on the severity of the disease. So that's our working hypothesis, and I mean we are trying to figure out if we are in the right track on that.
Thank you. That was interesting. Thank you a lot again. So if there are no other questions, I guess we can end this talk, and we end actually the second day of our Fair February. And the next appointment is going to be next Wednesday, when we will start the week 2 about computation and welfare policy making. Shahzad will be the speaker that will run the introduction for next week. The first appointment is on Wednesday, 3rd February. So we hope to see all you there. And thank you again for your participation.